Hello everyone. So in this pre-lecture tutorial, we're going to talk about how it is that chemists measure enthalpies of reaction. And so what it comes down to is measuring heat exchanges between the system and the surroundings. And so that particular branch of experimental chemistry, if you will, is what we call calorimetry, which again is all about just measuring heat transfers. And calorimetry is carried out in instruments that we call calorimeters, which again are designed in such a way that we can measure transfers between the system and the surroundings. Now, as it turns out, there are two different modes of calorimetry, if you will. There's constant pressure calorimetry, which we will actually discuss first, and then there's also constant volume calorimetry, which we will discuss second. And so let's talk a little bit about how constant pressure calorimetry works first, and then we'll go ahead and take an example problem. So as you can see, basically the constant pressure calorimeter can actually be quite simple. As a matter of fact, you can actually make them out of a pair of coffee cups, one nested inside the other. Essentially how it works is you're going to have a reaction mixture, and typically this reaction mixture involves aqueous solutions. And so that's why inside the coffee cups you see liquid, because we should have either an aqueous solution already in there that we'll be adding another reactant to, or it could be water into which we're going to dissolve two reactants. But in any case, you have an aqueous environment inside of that coffee cup. Now, obviously, we want to try and keep the reaction mixture as homogeneous as possible, and so that's why there is a stirring element within the calorimeter. And obviously we need a way to actually measure the production of heat or the intake of heat if it happens to be an endothermic reaction. And so that's why we have a thermometer actually sticking into the calorimeter as well. Now, obviously we want to choose materials to make our calorimeter that are good insulators. So this way any heat that's produced is fully measured. There should be negligible heat loss. Or in the case that there isn't negligible heat loss, then we actually have to measure up front how much heat is being lost to the calorimeter. But in most cases, when you're dealing with coffee cup calorimeter experiments and coffee cup calorimeter problems, it's assumed that the calorimeter is well insulated and that you have very little loss of heat to the calorimeter. And so in general, right, the way that we actually calculate the enthalpy of reaction is by using the following equation. Basically, the heat that is actually transferred either from system to surroundings or surroundings to system would actually be the product of the mass of either a component of the system or of the solution. We'll get more into that in a little bit as we start working through the solution to our example problem. A quantity called the heat capacity. All right, and what the heat capacity is, so again, just to recap, this is mass. The C is the heat capacity. And the heat capacity is a measure of the responsiveness of the material to heat. And so, for example, metals tend to be very responsive to heat. They heat up and cool down quite quickly, and so their heat capacities are very small. Water, on the other hand, you need to apply a fair amount of energy to get its temperature to change, and so water has a higher heat capacity as compared to metals. And finally, to get back to our equation, we're going to multiply the mass times the heat capacity times the change in temperature. So again, this is going to be the final temperature of the system, from which we're going to subtract the initial temperature of the system. Now, another note that I'd like to make regarding the heat capacity is this heat capacity is sometimes given in molar amounts. So basically a certain number of joules per mole per degree Celsius. Or it could also be given as what we call the specific heat capacity, and the specific heat capacity is usually measured in joules per gram degree Celsius. So again, here it would be per mass of the substance as opposed to the molar heat capacity, which is measured in joules per mole per degree Celsius. Now, again, this heat transfer, the way that we're going to use this equation within the confines of coffee cup calorimetry is when we measure the temperature change using the thermometer, that's going to be the temperature change for the solution. And so that affords us the opportunity of actually measuring the heat transferred to the solution or transferred from the solution. So that means we'd need the mass of the solution times the heat capacity of the solution times the temperature change of the solution. Notice that the variables must match each other. So all of these quantities all relate to the solution. But the way that it works is our frame of reference, if you recall back when we introduced the thermochemistry chapter, our frame of reference are simply the products and the reactants of the chemical system. The solution, in this case, so this would actually be considered our system. The water that makes up the solution actually represents the surroundings. So that means that if I'm going to calculate the heat generated by the reaction or lost by the reaction, I have to equate it to the heat that's either gained or lost by the surroundings or by the solution, because the water again represents the solution phase of our system. But any heat that is lost by our system must be gained by the surroundings, or vice versa. Any heat that is actually gained by our system must be lost by the surroundings. And so as a result, basically that means that there is a negative sign here, right, because of that inverse relationship. And so that would mean that our heat of reaction is actually negative mass of the solution times heat capacity of the solution times the temperature change of the solution. And so let's apply that to our example here. I have sodium hydroxide and hydrochloric acid, both of them at 1 molar concentration. And I'm going to mix 50 milliliters of the acid with 50 milliliters of the base. I'm given the initial temperature, which is 25.5 degrees Celsius, and the final temperature, which is 32.2 degrees Celsius. I'm being asked for the enthalpy in kilojoules per mole of hydrochloric acid. I'm to assume that the specific heat capacity of the solutions would be 4.184 joules per gram per degree Celsius. I'm also given separate densities for the acid and the base. And so what I'm going to need to do is find each of these particular quantities. Now again, as it turns out in the problem, they gave me the specific heat capacity of this solution, which I'm assuming is going to be 4.184 joules per gram per degree Celsius. I'm also given a way to calculate the temperature change. So basically that would be the final temperature of 32.2, and I'm going to subtract from that 25.5, which is the initial temperature. So that would be 32.2 degrees Celsius minus 25.5 degrees Celsius. Now, I need a way to actually calculate the mass of the solution. So basically what I'm going to need to do is actually find the mass of the hydrochloric acid. Well, for that I'm going to need the density. And so I have 50 milliliters of the hydrochloric acid times 1.02 grams per milliliter. And to that I'm going to add 50.0 milliliters of the sodium hydroxide. Actually, no, let me keep these terms separate so I don't mix them up. So I'm now going to calculate the mass of sodium hydroxide. So that would be 50 milliliters times 1.04 grams per milliliter. I would have to add both of these terms in order to get the mass of the solution. So, to this product, I'm going to add 50.0 milliliters of the hydrochloric acid times 1.02 grams per milliliter. I'm going to also add to that 50.0 milliliters times 1.04 grams per milliliter, so that I can calculate the overall mass of solution. And so if I go ahead and carry all of that out, I get negative 2,887.3784 joules, because the grams would cancel, the milliliters cancel, and my degrees Celsius would also cancel. But I'm being asked for the enthalpy in kilojoules per mole of hydrochloric acid. So again, remember, because I'm under constant pressure conditions, then the heat generated by the reaction should be Q at constant pressure. Also, since this heat is being lost by the system, that's why we have this negative sign. And so what I'm going to need to do now is actually go and first off convert this to kilojoules. Okay, and then I'm going to have to divide this by the number of moles of the hydrochloric acid. Well, I can find that from the molarity. So basically this would be dividing 50 milliliters of the hydrochloric acid. I'm going to convert these milliliters to liters and multiply that by the molarity of the hydrochloric acid in moles per liter. So if I go ahead and cancel my units and do that math, I actually end up with negative 57.7 kilojoules per mole of the hydrochloric acid. All right. Now, let's take a look at an example of constant volume calorimetry. Now, constant volume calorimetry is similar to constant pressure calorimetry, but with a few differences. Here, all right, these types of setups are actually best used for combustion reactions. Okay, and the way they work is whatever it is that you want to combust, you're actually going to put in this inner compartment of the calorimeter. The inner compartment is called a bomb, and so as a result, they tend to call these calorimeters bomb calorimeters. And so what you're going to do is you're going to put it in there, and this bomb is actually evacuated, and then inside of this bomb, you're going to put oxygen gas. So this way, you have an oxygen environment surrounding the sample that you want to combust. Then you're going to place that whole thing inside this tank of water, and you're going to go and you're going to plug in these electrical leads, and when you're ready, you push this button, and basically a spark will actually ignite inside the bomb, causing the oxygen to ignite and the combustion reaction to proceed. Any heat that's evolved from the combustion would then travel from the bomb to the surrounding water, and you're going to measure the temperature change of the water. Now, as you can see, there are a lot of different parts to this type of setup. And so as a result, whereas in coffee cup calorimetry, we sort of made the assumption that the calorimeter did not really take in any of the heat that was produced, it's a little unrealistic to assume that all of these different parts will not in some way, shape, or form absorb some of the heat that's evolved from the reaction. And so oftentimes for these constant volume calorimetry problems, the key piece of information that you need is the heat capacity of the calorimeter. So for example, here in this particular problem, I'm told that I'm going to combust 2.5 grams of toluene in a bomb calorimeter whose heat capacity is 4.15 kilojoules per degree Celsius. They give you the means by which to calculate the temperature change, and you're supposed to find the change in internal energy for the combustion of toluene in kilojoules per mole of the toluene. So recall, under constant volume conditions, the change in internal energy is the heat exchange under constant volume. But again, basically what's going to happen is any heat that is actually generated by the reaction is going to be lost to the calorimeter. And so that means that the heat of reaction is going to equal the negative heat that's actually absorbed by the calorimeter. And so what you're going to do is you're going to go and you're going to try and calculate this quantity Q cal. As it turns out, Q cal is actually not that bad to calculate, because all you have to do is take the heat capacity of the calorimeter and multiply that by the temperature change of the calorimeter, again, provided that you have the heat capacity for the calorimeter given. And so in this particular case, that's going to be 4.15 kilojoules per degree Celsius. That's our given heat capacity. And you're going to multiply that by the temperature change, which would be 45.4 degrees Celsius. And from that, I'm going to subtract 22.5 degrees Celsius. If I go ahead and do this math, I end up with negative 95.035 kilojoules. Now, keep in mind that that's the amount of heat that we generated from 2.5 grams of toluene, and I'm asked for the change in internal energy in kilojoules per mole of toluene. So these 95.035 kilojoules of heat that were given off from 2.5 grams of toluene. If I want to convert this change in internal energy to moles, then I would have to use the molar mass for toluene. I'll go ahead and leave it to you to verify that this is the correct molar mass for toluene, but that would be 92.13 grams per 1 mole of toluene. And if I then do this math, I end up with approximately negative 3.50 times 10 to the third kilojoules per mole. So that's the amount of heat that's actually given off from the combustion of 2.5 grams of toluene. So this is going to be a topic that we're going to spend a couple days on. Go ahead and work the follow-up assignment. Obviously, read the corresponding section of the book so that what I've given you in this pre-lecture tutorial makes a little bit more sense and you can see the context behind it. Again, if there are any questions, by all means email, and we will speak in class this week. Have a good night.